Welcome, pre-calc honor students, to section 9.3, Law of Sines, where we're going to use the law of sines to find unknown parts of triangles. We branch out from the right triangle to a general triangle, like we did with the area formula last section. Now, last section we developed that area formula. We call it K, where K equals 1/2 the product of any two sides times the sine of the angle between them. So you could set it equal to 1/2 AB sine C, or 1/2 BC sine A, or 1/2 AC sine B. And then you can take and divide all three expressions by 1/2 ABC. And let's see what happens when we do that. We get the law of sines, because if you take this 1/2 ABC and divide it here in this first expression, you're going to see the A and the B and the half cancel out, and you're left with sine C over C. That's what I have down here. If I divide this one by 1/2 ABC, we have the B and C canceling out, and the half, and so you get sine of A over A. And over here, the A and C cancel out, you get sine B over B. So that's the law of sines. Now, in English, this means the sides are proportional to the sine of their opposite angles. So when you come up with a straight triangle that isn't labeled A, B, and C, let's just say it's triangle QBR, and notice our convention here of using the uppercase letters for the vertices, the angles of the triangle, and the lowercase letters for the side opposite that given angle. So here's little q, little r, and little b. So you can set up all sorts of proportions. And so q is to r, as the sine of q is to the sine of r. So you don't always have to put the sides on the top or the angles on the top. If you're looking for angle b, you could say sine of angle b. You can't just say b is to r. You have to say the sine of angle b is to b, as the sine of r is to r. Now here's our first example. A civil engineer wants to determine the distances from point A and B to an inaccessible point C as shown. See, the river runs through the triangle, so he can't get there. So he takes some measurements here. From direct measurement, the engineer knows that AB equals 25, this distance. That's one side of the triangle. And angle A is 110, and B is 20 degrees. So from this, he wants to figure out sides A and B. Well, let's look through this. First of all, when you're given two angles of a triangle, you get the third from the idea that the sum of the angles equals 180. So we can get angle C by subtracting the sum of these two, 110 and 20, from 180 to get 50 degrees for angle C. Then we can go ahead and set up the law of sines. To find A is to the sine of A as C is to the sine of C. Because I picked C and sine of C because that's one where we know both the side and the angle opposite of it. So A is to the sine of 110 is 25 is to the sine of 50. Solve for A and you get 30.7. Notice B is done similarly. B is to the sine of B as C is to the sine of C. And we get to C sine B over sine C. So if you put this in your calculator, you can just go ahead and hit re-entry and change the 110 to a 20. And it should be a lot easier to calculate the second part then. Now, I want to talk about the two different types of givens in where you can use law of sines right away. And that's like the angle side angle case that we just looked at, where you have a side and the angles on either side of it. And it's very similar to the side angle angle case, where you have a side and an angle attached to it and an angle opposite it. In either of these two cases, we're going to find it's easier than the side angle because you can, if you're given two angles, you can find the third angle with the idea that the sum of the angles equals 180 degrees. Then you can use law of sines to find the other two sides. We're going to find out that it's a little trickier, though, when you do side angle. Okay? So when we go to these type of examples, let's do a practice one first, illustrating this ambiguous case. We're going to explore these similar situations, all example of side angle, where you have two sides of a triangle, but the angle given is not between the two sides. So in each of these three cases, I have angle A is 30 and side B is 10, and side A is given, and it changes from 4 to 5 to 6. So I want to show you how we can do these on GeoGebra. And you might want to follow along with your own GeoGebra on the side, because you're going to find it's a nice way to illustrate the problems you submit and to explore word problems in the future. Okay, here we go. Here's GeoGebra. We're not going to use the algebra aspect of it so much, but I do generally like to keep this diagram up so I can easily click on exactly the thing I want to change if I have to. I'm going to go to a view of no axes. So click on the axes, take those away. And we start off with a point A. So let's put that down. There's our point A. And that looks okay. And back to our circle and radius. Circle through center with a radius. Click on A. And it calls up the radius, and we want that to be exactly 10. And notice that's probably going to go way off of our diagram. So we can do a little zoom out. Maybe just once. Yeah, that's good. And maybe move the screen around a little bit. Move the graphics view like that. And now I'm actually going to plot point C as a point on this circle. So make sure that her circle lights up when you do that. I'm going to rename that right away to point C. And sure enough, we're going to find that this segment should be 10 long. Because there's any point in the circle, and yes, there's 10 long. But that is actually the length of B, so I'm going to rename that as well as length B. Okay. Now we also want to get the angle A established, because right now all we have is just side B is length 10. That's good. Now we want to get angle A of 30 degrees. So I'm going to want to rotate this point C about this point A, about the circle, to come up with a 30-degree angle. Here we go. Rotate object about a point by an angle. We're going to click on the object here, C, then click on the point A that we're going to rotate about, and then say we want to rotate clockwise 30 degrees. There you go. And now if we make this ray that starts at A and goes through C prime, I think you're going to find that this isn't exactly a 30-degree angle. So let's measure it. Measure the angle. Let's measure this angle by clicking on C, A, and C again, C prime. There we go, there's our 30-degree angle. And we find we can move this around like that. We can move point A around, everything like that. We're not going to need C or the circle anymore, so I'm going to unhighlight those. Unhighlight C prime and highlight the circle. And now you can see that we've got the two of the parts of the given situation that are common to all three situations, where we have side B equals 10 and angle A equals 30 degrees. Okay? Now what to put inside A is 4, 5, and 6. So this is where I'm going to use a slider to let A range. And you have to click somewhere in the space. Let's click right there. We're going to call it A. And we want to have it go from 0 up to, let's say, 12. Increment rate 0.1. That should be fine. So now A slides along just fine, because A is going to be the radius of the circle we make at C. Side A is going to be attached to points C and B, and it'll be opposite angle A over here. So to make side A now, I'm going to draw a circle centered at C with radius of A. So I go to my circle generator again, circle, center, and radius. Oopsie, cancel that. Again, it threw out a point B here for some strange reason. Okay. Here we go. Circle, circle through center and radius. There we go. Now select center and enter the radius, which don't just enter a number and put in little a, because then we can change it with our slider. So now you can see how our slider will change. Oh, it's still on point generator or something, or circle generator. Cancel that. Sorry, you have to go to the grabber tool here, the pointer tool. And now we can slide a, oh gosh. Okay, we gotta get this whole slider somewhere else. Oh, that's fine. Now A changes from 0 up to whatever size we want. And for the first example, we want to look at what happens when A equals 4. And you can see when a equals 4, it doesn't quite stretch far enough to actually coincide here with side C. So a equals 4 is not big enough, and we get no solution. Now I'm going to crank this up to a equals 5. There, a equals 5. Boom. Now you get a solution. In fact, we can ask the calculator where the intersection of these two things are. So let's go to intersecting points. Intersect these two objects, the circle and this ray. And we get, there's our point B. Okay? Now in this scenario then, we end up with just one solution. And when we connect these two to make our final side here, and this is going to be side A, but it calls it side E. I'm going to rename this as, we'll call this A1. Just not confused with the A that we have over here. Now A1 should equal 5. It's supposed to equal 5. That's what the slider is right now. But I want to show you that we might come up with some other sides. In fact, let's measure this angle that results at angle B. I think you can tell what it looks like. C, B, A. And it even puts a little right angle symbol on there for you. Sure enough, it's a 90-degree angle. So that's our scenario when A equals 5. We get exactly one solution. Now, though, when we move the slider up to 6, now we generate this other point over here, this D point. And let's just call that, let's relabel that as B prime. Because it's like the, let's call it B2. B2. Because it's a second option. And I'm going to put a little dashed line in between that. Let's make the segment. And let's go to object properties on that. First of all, I'm going to rename it as A2 as an alternative answer for A. And also, let's look at the properties and just make it dashed so you can tell it's a different triangle. Style, figure, and dashed. Okay? So this is why it's called the ambiguous case, because sometimes you have no answers. Sometimes you have one, sometimes you have two. And watch what happens now as I crank up 6 even more. Oh, notice, here's our one answer of 123.56. Let's measure this other angle over here with the angle measure, C, B2, A. And then we also get this 56-degree angle. Notice how these two are supplementary to each other. Okay? Now, if we keep cranking up A, we keep getting two answers. There are two answers over and over again. Except when we get so big, then now we're back to one answer again. Anything basically over 10. When it got to 10, it created an isosceles triangle. And anything beyond that, then, we're just going to get the one answer for B. Okay? All right. Hopefully, then you can see the nature of the ambiguous case. And there's actually an exercise in your homework where you use a formula to figure out when you can predict when you're going to have each of these cases. The no solution case, one solution here at 5, two solutions, and then we're back to one solution then if it gets big enough. All right, back to the notes. So to review what we did here from GeoGebra, in that first case we had no solution. How could you do this without a picture? Well, if you set up the law of sines in this and go the sine of B is to B as the sine of A is to A, and substitute in there sine B equals B sine A over A, 10 sine 30 over 4, sine of 30 is exactly a half, so you get 5/4. Sine of B equals 5/4, that's impossible. Sine can't be bigger than 1. So that's why we get no solution there. In this next case, when let's A equal 5, and you set it up, you get the sine of B equals 1, and that's just the one answer at 90 degrees, as we saw. And then finally in case C, when A equals 6, now you get the sine of B equals 5/6, and you get two solutions. Because you get inverse sine of 5/6, the calculator gives you one answer, 57 degrees, but then the supplement for that also works. 180 minus 57 degrees equals 123 degrees. Okay, Now here's example 2. We've got triangle RST. And we're trying to figure out how to do this. If it's, again, it's a side-side angle case, the obnoxious, ambiguous case, where you got 126 degrees for angle S. Side S is 12, side T is 7. Determine the angle, whether angle T exists, and if so, measure all the possible angles. So try and make a picture of this. Now remember convention. Angle S is opposite side S. So it's hard to draw these two right away. Instead, focus on angle S and side T and connect those. And that's what I did in my picture. I connect the 126 degree angle with the side T equal to 7. And then draw this out here. And if this is about 7, I drew something that looked like it was about 12. And that's just a rough idea. Now I can use law of sines, except sine of T is to T, as sine of S is to S. Sine of T equals T sine S over S. So substitute in 7 for T and 12 for S and 126 degrees in for angle S. Make sure you're in degree mode. And sine of T equals 0.471926. So I take the inverse sine of that, and that gives me 28.2. I consider the supplementary angle, because whenever you use law of sines to find an unknown angle, you should be conscious of the fact that you might get a second answer. Thing is, though, in this case, if I take the supplementary answer of 151.8, that would be 2 obtuse angles. So I throw that one out, and I just keep the one case of 28.2. And we can see that in our picture, that if I have one obtuse angle here, there's no way that this angle T is going to be obtuse. Okay. Flange out.